In this lecture, we will see some more examples and applications of the Chernoff bounds. We will first talk about a problem called parameter estimation, and then we will define two special random variables and study their Chernoff bounds. And finally, we will see applications of these Chernoff bounds that we have derived, and they will be used in the following two problems. The first one is called set balancing, and the other is the normal fair coin flip. Let's start. Okay, so for parameter estimation, suppose that in Taiwan, an unknown fraction of people are now infected with a certain disease, for instance, the COVID. And the DNA test can confirm if a certain person is infected with the disease or not. However, the test is expensive. Suppose that we want to find out what is the fraction of people or rough estimate of the fraction of people in Taiwan that are infected. So is it possible that we can only do experiments or DNA tests on a small number of samples so that we can have relatively good reliability on the estimation that we obtain? So this is the so-called parameter estimation problem. So for instance, let's say we are going to perform n experiments. So we will take among all the people in Taiwan, n of them, and then we call them the samples. And after doing the experiment, let's say x of them are infected. So x of these n samples are infected. So somehow we can find out what is the fraction of the samples that are infected samples. So we let Q to be equal to x over n. On the other hand, we defined P to be the actual fraction of infected people over all the people in Taiwan. So if we perform enough experiments, if we have large enough n, then it turns out that Q should be very close to P. In particular, if n is like all the people in Taiwan, then Q will be equal to P. So some possible questions that we may ask is, so how many samples should we use so that P will be 99.9% likely to be within the range of Q plus or minus 0.001? Or suppose that we have only money for 1,000 samples. And how much confidence, how much chance that we can say that P is within Q plus or minus 0.001? Or suppose that we have 5,000 samples now, and then what is the delta that we can claim so that 85% of the time the actual probability of infection, this P, is within Q plus or minus delta? So here we see that in these questions, we will have some parameters like what is the probability that P is within a range of Q plus or minus something. So there is a value here, and also we will have the number of samples that may be changing, and also the value plus or minus delta, the delta value that we may be changing. So here we first define the concept of confidence as follows. If P is within the range of Q plus or minus delta with probability greater than or equal to 1 minus gamma, then we say that P is within this range, Q plus or minus delta, with confidence 1 minus gamma. And here, in this part, we want to derive a relationship for n, the number of samples that we should make, delta, the value of delta here, which is talking about the range around the Q, and also gamma, which is related to the confidence value. So can we derive a relationship for n, delta, and gamma? Okay, so first of all, let us confirm the following fact. Suppose that we are taking samples such that we are taking samples with replacement. Then in such a case, there are going to be n samples taken, and for each sample, it has independent probability p to be an infected sample. And it turns out that x is the observed number of infected samples, so x will be a binomial random variable with parameter n and p. The expected value of x would then be n times p. Now we want to establish a relationship between n, delta, and gamma. So first, let us examine the case where p is not within the range of q plus or minus delta, and see what we can say about this case. Now when p is not within the range q plus or minus delta, there can be two possible cases. One is either p is too small, p is smaller than q minus delta, or the other case is p is too large, p is greater than q plus delta. Now when p is smaller than q minus delta, then it means that n times q will be greater than n times p plus delta. Now n times q is actually the value of x, although x is a binomial random variable with parameter np, but then x can be expressed as n times q because x over n is equal to q. So this is the actual value that we observed from our experiments. So nq is equal to x. And then what is np? np is the expected value of x. So n times p plus delta can be expressed as expected of x multiplied by 1 plus delta over p. And similarly, for our second case, when p is too large, then nq will be smaller than n times p minus delta. And this happens if and only if x is less than expected value of x multiplied by 1 minus delta over p. So when you see the form of this one and this one, then the first idea comes to you. This is the Chernoff bounds for the sum of Poisson trials. So we can apply the Chernoff bounds for sum of Poisson trials to bound what is the probability that p is not within q plus or minus delta. Okay, the probability of this occurring is simply the probability of the case that p is too small plus the probability of the case that p is too large. So this is one of the case and this is the other case. Now we can replace the first one by the Chernoff bounds that we have obtained from the previous lecture, and similarly the second one with the Chernoff bounds that we have obtained from the previous lecture for this case. Now by doing some algebraic simplification, we will see that the exponents here will have a p contained inside. In particular, let us focus on this case. This is minus np times delta over p squared divided by 3. So after doing some cancellation, this will be minus n times delta squared over p and then over 3. We don't know the value of p. This is some unknown parameter. So in order to make the formula so that we can have a certain claim, we will make a loose estimate by estimating that since p must be a probability value, so it is at most 1. So in that case, we can replace this term by a weaker bound by setting p to be equal to 1. So in that case, we have this term to be strictly smaller than e to the power minus n delta squared over 3. And similarly, this term, we will bound it by saying that this is smaller than e to the power minus n delta squared over 2. Now finally, if we set this term, this whole thing, to be equal to gamma, then we will see that the probability of p is not within q plus or minus delta will be less than gamma if we set this to be gamma. So in other words, the probability of P is within Q plus or minus delta will be greater than or equal to 1 minus gamma. And so we can have a certain relationship between N, gamma, and delta. So if we can fix, let's say, N and delta, so for instance, if we know how much samples that we can take, and then if we want to have a certain bound on this delta, then in that case, we can find out what is the confidence that we can claim. And similarly, if we have delta and gamma to be set to be something that we want to keep, then in that case, we can find out what is the number of samples n that we want to have in order to have the claim that the probability P is within Q plus or minus the predefined delta is greater than or equal to the predefined confidence 1 minus gamma. So this is about parameter estimation.